Welcome to our Quantum Deep Dive. Today we're embarking on a journey into a field that promises to redefine, well, the very limits of what computers can do. We're diving deep into the intricate world of quantum information science, and we're drawing insights from an incredibly comprehensive essay by Jorgo Schneeppert titled Quanteninformatik, die Zukunft der Computertechnologie.
Yeah, exactly. Our mission today is to really unpack the fundamental principles of quantum computing, look at its revolutionary potential, and also, confront the significant challenges that still lie ahead. It's a field that's not just about building faster computers, not really. It's about entirely new ways of solving problems that are currently, completely beyond our reach, almost unimaginable stuff.
Okay, let's unpack this then. Why do we even need quantum computing? I mean, classical computers have made incredible strides, right? Shrinking transistors down to microscopic sizes. Just think about the device probably in your pocket right now. But, as Jorgo Schneeppert points out, they're hitting some fundamental limits, both physical and technological. Have you ever stopped to wonder what happens when those tiny components start, behaving according to the bizarre rules of quantum mechanics?
Well, the core issue for classical computers is their binary nature. A bit is either a 0 or a 1. Simple as that. Quantum information science introduces the qubit. And this is where the fundamental difference really lies. What's fascinating, truly fascinating here, is that a qubit isn't just 0 or 1. Through something called superposition, it can actually be both at the same time, existing in this sort of weighted combination of states. Mathematically, you might see it as alpha 0 wrangle plus beta 1 wrangle. Now, don't let the Greek letters scare you off. Think of alpha and beta as like the weights or amplitudes that tell you the probability of getting a 0 or a 1 when you finally look at it, when you measure it. The really mind-bending part, though, is that it's not just a 50-50 chance until you measure it. It's somehow simultaneously both. And this capability, this leads to an exponential growth in processing capacity. Just think about it. A system with n qubits can simultaneously store and process 2 n states.
2 to the power of n, wow.
Yeah, that's where quantum parallelism comes in. It gets really interesting there.
So, okay, a quantum computer isn't just a slightly better, faster version of my laptop. It's fundamentally different using these quantum tricks. And this exponential power lets quantum computers tackle problems that are just, practically impossible for even the biggest classical supercomputers today.
Precisely.
Yeah.
Consider factoring large number.
Okay.
This is what underpins the security of so much of our modern encryption. Things like RSA.
Right. Online banking, secure websites.
Exactly. A classical computer would take, billions of years to factor a really large number used in encryption today. That makes it effectively secure. But a quantum computer, using something like Shor's algorithm, it could potentially factor them in polynomial time. Much, much faster.
Polynomial time. Okay, so practically speaking?
Practically speaking, it means current security mechanisms could be broken. And the truly chilling part, if you connect this to the bigger picture, is how it could unravel decades of secure communication retrospectively.
Retrospectively. You mean old stuff too?
Yeah, imagine encrypted data stored years ago suddenly becoming readable if someone gets a powerful enough quantum computer. That's the kind of silent revolution Shor's could bring.
That's a sobering thought. Okay, so beyond breaking codes, which is huge, where else does this exponential power really shine?
Well, another critical area is optimization. Think about complex systems like in logistics or financial modeling or material science. These often involve what we call NP-hard problems.
NP-hard. Those are the really tough ones, right?
The really intractable challenges for classical computers, yeah. Where finding the absolute best solution is exponentially harder than just checking if a solution works. Quantum computing promises a significant speed up for these kinds of problems.
And you mentioned simulating physical systems. That sounds incredibly exciting, too, like designing new drugs or materials.
Exactly. Imagine simulating molecules, simulating quantum mechanisms directly for new drug discovery, for advanced materials. On classical computers, this is only really feasible for very small, simple systems because the computing effort just blows up. It grows exponentially with the system size. It's like trying to model a whole rainforest by looking at just a few trees. Quantum computers, though, because they are quantum systems, they naturally follow quantum laws, so they're inherently much, much more efficient for these types of simulations. They're basically built to mimic quantum reality itself. Okay,
so we've talked about these almost magical properties of qubits, superposition, being in multiple states at once. But how do you actually, bottle that lightning? What else do we need to understand about how a quantum computer works beyond just superposition?
Right. Beyond superposition, Coherence is absolutely key. It's crucial. For a quantum system to actually perform calculations efficiently, it has to stay in what we call a coherent state. That means the quantum properties, the superposition, and entanglement are preserved. Any interaction with the outside environment, even the tiniest vibration, a stray magnetic field, a bit of heat, causes decoherence.
And decoherence is bad.
Decoherence is bad. It leads to errors. The quantum information gets lost. It basically collapses back into a classical state. This is honestly one of the biggest, hardest challenges in actually building quantum computers. It's like trying to hold a perfectly still soup bubble in a hurricane. And then there's entanglement. This is one of the most counterintuitive, maybe the weirdest, but also one of the most powerful quantum phenomena.
Einstein's spooky action at a distance.
That's the one, yeah. It describes this deep, instant connection between two or more qubits. Their fates are intertwined, linked, no matter how far apart they are physically. If you measure the state of one entangled qubit, you instantly know the state of the other one, even if it's miles away.
Instantly. Wow.
Instantly. It's fundamental to how many quantum algorithms work, and it's also crucial for things like quantum communication protocols, like BB84.
Ah, you mentioned the BB84 protocol. What exactly is that? Can you elaborate a bit?
Sure. BB84 is a groundbreaking method for quantum key distribution, QKD. It essentially allows two parties, let's call them Alice and Bob as usual, to create a perfectly secure cryptographic key. And the security comes from the laws of quantum mechanics itself. Any attempt by an eavesdropper, let's call her Eve, to intercept or measure the quantum states being exchanged inevitably disturbs them.
So you can tell if someone's listening in.
Exactly. The disturbance is detectable. So Alice and Bob know if their key has been compromised. It's security basically built into the fabric of physics itself. Pretty neat.
That is fascinating. Security by physics. Okay, so we have these amazing qubits operating with superposition and entanglement, getting incredible coherence. But how are they actually built? What do they look like? What are the physical things?
Right, the physical realization. That's the engineering marvel, isn't it? There isn't just one way. There are several leading contenders, these different approaches, each with its own, ingenious design and unique set of challenges. Probably the most widely discussed right now are superconducting qubits. These are the ones companies like IBM and Google are heavily focused on.
Okay, superconducting, like zero resistance.
Kind of. They use tiny superconducting circuits. They're incredibly fast-performing operations in nanoseconds. But the big challenge is their environment. They need incredibly low temperatures.
How low are we talking?
We're talking around 10 millikelvin. That's near absolute zero, colder than deep space.
Wow. Why so cold?
To minimize thermal noise, the heat that causes decoherence. But yeah, it makes the whole system incredibly complex and expensive to build and maintain.
Near absolute zero. That sounds like an immense hurdle. Are there other ways that maybe don't require quite such extreme cooling or offer different trade-offs?
Oh, absolutely. Then you have ion trap qubits. Pioneers in this area, like IonQ and Honeywell, they literally suspend individual charged atoms, ions, using electromagnetic fields, like tiny magnetic bottles. And they manipulate these trapped ions very precisely using lasers.
Individual atoms. That sounds precise.
Extremely precise. And the big advantage here is they boast very long coherence times. Their quantum states last much longer, which makes them potentially more stable for calculations.
But there's a downside.
The downside is they're generally slower to operate compared to the superconducting ones, and it's technically very challenging to scale them up to trap and control hundreds or thousands of ions perfectly. And then there's another really interesting approach. Topological qubits. Microsoft is investing heavily in this area. These are theoretically highly resistant to errors. They're based on these exotic things called quasi-particles, which emerge from the collective behavior of electrons in certain materials under specific conditions. The idea is that the quantum information is stored in the topology, the sort of braiding of these quasi-particles' paths, which makes them inherently more robust against local disturbances and decoherence.
Theoretically robust, so what's the catch?
The catch is, finding these quasi-particles and demonstrating a working functional topological qubit experimentally is still a major research hurdle. We're really talking about bleeding-edge physics here. It's a long-term bet.
Right. So each method is this incredible feat of engineering, really pushing the boundaries, trying to harness these delicate quantum principles in a practical way. It's a fascinating race, isn't it, to see which technology or maybe combination of technologies will ultimately pave the way for a truly useful universal quantum computer.
Yeah.
Okay, so with these incredible building blocks sort of in place, or at least being developed, the next logical question for our listeners has got to How do we actually program these machines? How do you tell a quantum computer what calculations to perform?
Yeah, good question. Just like classical computers use logic gates, A and D or NOT gates acting on bits, quantum computers use quantum gates. These perform specific operations on qubits. For example, there's a gate called the Hadamard gate. What it does is take a basic state, like a definite 0 or 1, and put it into a perfect superposition, creating that both 0 and 1 at once state we talked about. Then there's something like the CNOT gate, which stands for controlled NOT. It performs a negation, like flipping a 0 to a 1 or vice versa on one qubit, but only if another control qubit is in a specific state, usually the state 1. So it links qubits together. Is that related to entanglement?
Exactly. The CNOT gate is one of the fundamental ways we create entanglement between qubits. These gates and others allow us to perform calculations that are just simply not possible with classical systems, manipulating these quantum states and leveraging things like interference between them. And the real computational horsepower comes from what we call quantum parallelism. Because of superposition, a quantum computer can, in a sense, explore many possibilities simultaneously. Imagine trying to find your way through a huge maze. A classical computer might try one path, hit a dead end, backtrack, try another path, and so on.
Right, step by step.
A quantum computer, because its qubits can be in superposition, can sort of explore all the possible paths at the same time. This is where that potential exponential speedup comes from for certain problems.
And this leads us directly to the algorithms, the specific recipes or instructions that unlock this quantum power. This is where it starts to get really interesting, application-wise. Absolutely. And the most famous, or maybe infamous, depending on your viewpoint, is Shor's algorithm. Peter Shor developed it back in 1994. As we touched on earlier, it's famous because it can factor large numbers in polynomial time.
Which, again, is the threat to things like RSA encryption.
Exactly. It means a sufficiently powerful quantum computer running Shor's could break most of the public key encryption we rely on today, potentially in a practical time frame, like hours or days instead of billions of years. This really highlights why the development of post-quantum cryptography, new encryption methods resistant to quantum attacks, is so urgent. It's not a future problem, it's something we need to prepare for now.
Okay, so Shor's algorithm is about breaking codes, unlocking secrets. What about finding things, like searching through massive amounts of data?
For that we have Grover's algorithm, developed by Grover in 1996. Now, Grover's offers what's called a quadratic speedup, not exponential like Shor's. It reduces the time to search an unsorted database from ON, meaning you might have to check every item in the worst case down to up OS, the square root of n.
Okay, quadratic. So not as dramatic as exponential, but still faster.
Still significantly faster for large databases. Imagine searching a list with 1 million items. Instead of potentially 1 million checks, you'd need something closer to 1,000.
That's still a big difference.
It is, and its applications are quite broad. Faster database searches are the obvious one, but it can also be used for optimizing problems that can be framed as a search and maybe even enhancing certain machine learning tasks by speeding up how data is processed or searched.
Interesting. And beyond these two big names, Shor and Grover, are there other important quantum algorithms being developed?
Oh, yes, definitely. There's a growing zoo of them. For instance, there's the HHL algorithm, which is designed for solving systems of linear equations exponentially faster than classical methods in some cases. That could be huge for fields like data analysis, engineering, and financial modeling. And another crucial component is the quantum Fourier transform, or QFT. It's actually a key subroutine within Shor's algorithm itself, but it's also powerful on its own for things like signal processing and identifying patterns in complex quantum data. So if we zoom out again and connect all these algorithms to the bigger picture, the potential applications really start to look vast. We're talking about optimizing incredibly complex systems, supply chains, financial markets, traffic flow for unprecedented efficiency. We're talking about vastly accelerating machine learning, maybe enabling new types of AI by processing massive data sets in fundamentally new ways, simulating molecules for revolutionary new drug discovery and material science, as we mentioned, designing catalysts, creating better batteries, and of course, enabling truly secure communication through those quantum cryptography protocols like BB84. The list keeps growing.
This all sounds incredibly powerful, really transformative, almost like science fiction becoming reality. So the obvious question is, why aren't quantum computers running everything already? What are the biggest hurdles, the roadblocks in bringing this technology into the mainstream, into, daily use?
Yeah, it's a fair question. The challenges are significant and they're kind of interconnected. The primary one, as we keep coming back to, is decoherence.
Maintaining that fragile quantum state.
Exactly. Keeping those qubits coherent, preserving their superposition and entanglement for long enough to actually perform complex computations is incredibly difficult. They're just so sensitive to any noise from their environment. That's why many of the current approaches need those extreme conditions, like the near absolute zero cooling down to around 10 millikelvin, which is about minus 273 degrees Celsius or minus 460 Fahrenheit.
Just to keep them quiet enough to think, basically.
Pretty much. To minimize that thermal interference and allow the quantum state to last for maybe just microseconds or milliseconds. It's like trying to conduct a symphony during an earthquake. Then, another huge hurdle is error correction. Quantum errors happen constantly due to decoherence and imperfect gate operations. But unlike classical bits, you can't just copy a qubit to make backups because of a fundamental rule in quantum mechanics called the no-cloning theorem. You simply cannot make a perfect identical copy of an unknown quantum state.
No copying. So how do you fix errors?
It means we have to develop these incredibly sophisticated quantum error correction codes. Things like the surface code are leading candidates. The basic idea is you encode the information of one logical qubit, the one you actually want to use for computation, across many, many physical qubits.
Many physical qubits for one logical one.
Yeah, potentially thousands or even more physical qubits working together in a complex, redundant way just to protect one single logical qubit from errors and keep it stable long enough to be useful. It's a massive overhead.
Thousands for one.
Wow.
And that ties into the next challenge, I guess, which is scalability.
Exactly. Scalability is the third major roadblock. The most powerful quantum processors today have, a few hundred physical qubits, maybe edging towards 1,000 in some prototypes. But to achieve what we call universal fault-tolerant quantum computing, the kind that could reliably run Shor's algorithm on large numbers or tackle truly complex simulations, we're likely talking about millions of high-quality, interconnected physical qubits.
Millions?
Millions. And managing all of them, keeping them coherent, correcting errors across that vast system, it requires monumental breakthroughs in fabrication, integration, wiring, control systems, everything. But despite these really daunting challenges, I should stress that hardware development is progressing at an astonishing pace. Google's demonstration of quantum supremacy back in 2019 was a big moment. Their Sycamore processor performed a very specific calculation in minutes that they argued would take the world's best classical supercomputer thousands of years.
Right, that specific, maybe not practically useful task, but it showed potential.
Exactly. It was a proof of concept milestone. And IBM, IonQ, Microsoft, Rigetti, and many others are making huge strides too. They're constantly increasing qubit numbers, improving coherence times, reducing error rates, pushing the boundaries year after year. The progress is real.
Okay, so it's clear then that quantum computers aren't just going to suddenly replace our laptops or phones overnight. That's not the trajectory. So what does the future of computing look like? With quantum technology becoming part of the picture. For you, the listener, how might this play out?
Well, the most likely, certainly the most immediate path forward seems to be hybrid quantum classical systems.
Hybrid, meaning they work together?
Exactly. Think of quantum computers acting as highly specialized co-processors or accelerators. They'll tackle only the parts of a problem where quantum mechanics offers that exponential advantage, the really hard quantum simulation part, or the core factoring step, or the complex optimization. Meanwhile, classical computers will handle everything else. Data input-output, pre-processing, post-processing, orchestrating the overall workflow. They'll do what they do best. We're already seeing this model emerge. Companies like IBM, Google, Amazon, Microsoft Azure, they already offer cloud-based access to their quantum processors. So researchers and businesses can start experimenting with this kind of hybrid approach today, programming quantum tasks through the cloud without needing their own multi-million-dollar quantum hardware in the basement.
Right, accessing it as a service. Okay, beyond the tech itself, what about the bigger picture? The broader societal implications, the ethical considerations. What do we as a society need to be thinking about as this powerful technology matures?
That's crucial. The biggest, most immediate concern for everyone is definitely the threat to current cybersecurity. We keep coming back to Shor's algorithm for a reason.
Because it breaks today's encryption.
Because it breaks today's standard public key encryption. If, or perhaps when, large-scale, fault-tolerant quantum computers become available, they could potentially decrypt vast amounts of currently secure data, historical government communications, corporate secrets, financial transactions, maybe even personal messages stored today. They could also break the security underpinning things like blockchain and cryptocurrencies.
So what's the defense?
The defense is post-quantum cryptography, or PQC. Organizations like NIST, the U.S. National Institute of Standards and Technology, are in the final stages of standardizing new encryption algorithms that are believed to be resistant to attacks from both classical and quantum computers.
So it's a race to upgrade our digital infrastructure before the code breakers arrive, essentially.
That's a pretty good way to put it. Yeah, it's a critical race against the clock.
Okay, so cybersecurity is huge. What about other implications? How this tech might be used? Who gets access?
Right, that opens up significant ethical and regulatory questions that people are already starting to grapple with. Should the development or use of powerful quantum computers be regulated somehow to prevent misuse, perhaps for cracking codes maliciously or developing new kinds of weapons? That's a tricky one. How do we ensure that access to this incredibly powerful technology is managed fairly? How do we avoid it just exacerbating the existing technological divides between rich and poor nations or between large corporations and smaller players? Could it create new forms of inequality?
These are big questions. Are there efforts to address this?
There are positive initiatives emerging. For example, things like the Quantum Open Source Foundation, QOSF, are working to make quantum computing knowledge and tools more accessible worldwide, trying to foster a more collaborative and equitable development path. But yeah, these are complex societal discussions, and the answers will likely evolve alongside the technology itself.
So, to kind of wrap up this deep dive, bring it all together. Quantum computing isn't really about replacing the computers we use every day, not directly anyway. It's about creating an entirely new class of specialized tools. Tools capable of solving certain types of problems that are currently, for all practical purposes, impossible for any classical machine we can imagine.
Yeah, that's a good summary. The underlying principles, superposition, entanglement, quantum parallelism, they are truly revolutionary. They offer a fundamentally different way to compute. And while those challenges we discussed, decoherence, error correction, scalability, are still very real and very difficult, the progress is undeniable. The advancements in hardware, in algorithms, and just in our fundamental understanding are happening incredibly quickly. It makes this one of the most exciting and potentially impactful fields of research right now. Its potential in cryptography, in optimization, in material science, drug discovery, AI, it's immense. It really does promise to redefine the boundaries of what humans can compute, and ultimately what we can understand and achieve.
And this fascinating deep dive was inspired by that comprehensive essay from Jürgen Schneeppert, Quantum Informatik, die Zukunft der Computertechnologie. If you want more information, want to explore the depths of quantum informatics yourself, you can visit schneepet.de. That's SCHNEPET.de. Thank you so much for joining us on this quantum deep dive. After all we've talked about today, here's something to think about. What problem do you think quantum computing could solve that seems utterly impossible right now? Keep mulling that one over. Until next time, keep diving deep.